Global logistics networks, international banking, and database queries numbering in the hundreds of millions share one strict requirement: they cannot tolerate a single second of downtime. If the servers stop, the shipments halt, the transactions fail, and the business stops dead. For decades, the standard response to this growing demand was simply building larger, more centralized physical powerhouses. Organizations bought industrial-scale, standalone mainframes, packing as much processing power as possible into a single chassis. No matter how powerful that single machine is, it carries a fatal architectural flaw. A standalone computer inherently represents a single point of failure. If a crucial hardware component dies, the system crashes. Even if the hardware runs flawlessly, the IT team eventually has to install mandatory software updates or replace aging parts. To do that, the entire system must be taken offline, bringing those global operations to a halt. Achieving true 24/7 reliability is impossible if we rely on building one indestructible machine. The physical limits of hardware require a completely different architectural approach. You might think the obvious alternative is to wire two computers together to share the workload. But when both independent servers attempt to write to the exact same database record simultaneously, their data packets collide and shatter, resulting in corrupted information. To solve this scaling problem, IBM created a clustering technology called the Parallel Sysplex. This architecture links up to 32 independent z/OS server images, combining discrete physical hardware components into a single cooperative unit. The engineering pillar that makes this Sysplex possible is the coupling facility. Instead of a standard drive, it operates as a high-speed shared memory scratchpad. It organizes incoming requests, allowing all 32 systems direct concurrent read-write access to shared data without corrupting records. By solving the data collision problem, the coupling facility lays the groundwork for dozens of independent machines to safely chew through a single global workload. To maintain the illusion that these 32 servers are actually a single machine, there is another physical hurdle. Every event occurring across these separate pieces of hardware must be perfectly sequenced in time. To achieve this, the cluster relies on a Sysplex timer, or server time protocol. This synchronizes the time-of-day clocks across all clustered servers down to the microsecond, ensuring that if multiple systems update a database, every action is stamped in exact unison. With time perfectly synchronized, the Sysplex actively manages the flood of incoming global business requests using a component called the Workload Manager. The Workload Manager acts as an autopilot, dynamically balancing incoming transactions across the 32 servers based on available capacity. If a node suddenly dies, the Sysplex Failure Manager instantly reroutes its work to healthy servers, dropping 0 tasks without human intervention. Perfect microsecond synchronization, combined with automated failure management, creates a self-healing system that actively refuses to go offline. Despite the immense physical complexity of 32 interconnected synchronized servers, the human experience in the control room is completely streamlined. The architecture provides a single point of control. A system programmer can log into one logical network entity and manage all 32 cloned systems at once, typing commands as if they are interacting with just one machine. This architecture provides the foundation for rolling maintenance. An IT team can intentionally take a server completely offline to swap out hardware or install a new software release. Because the cluster shares the workload, the remaining active systems seamlessly absorb the traffic. IT staff can introduce new applications or replace infrastructure on a schedule that fits the business, entirely invisible to the end user. True enterprise reliability is an engineered illusion. It relies on the understanding that building one computer that never fails is impossible. Real continuous availability comes from uniting many machines to absorb and hide failure entirely.